In this section, we are going to consider some properties of program graphs. One is a property of being a deterministic system, that the program gives the same result whenever it is executed on the same memory. Another is that of being an evolving system, that the program continues to operate all the way to the end. Perhaps it does not reach the end because it enters into a loop, but it will not get stuck at any node except the final one. To be a bit more precise, a program graph is deterministic whenever we execute the program twice from the same initial configuration. Then we end up in the same final configuration with the same final memory, and we have performed the same actions along the way. There is a simple, sufficient test to check for this, namely that every node has at most one edge leaving it upon which the action is defined for the memory at hand. That this condition is sufficient to ensure that the system is deterministic is expressed by the proposition here. The proof is in the book. Turning to evolving systems. A system is evolving whenever it can continue to take an execution step until it has arrived at a final configuration. We express this by saying that a computation sequence into a configuration that is not final can be extended with one more step. Again, there is a simple, sufficient test for this to hold, namely that every node must have at least one outgoing edge whose action is defined on the memory at hand. That this condition is sufficient to ensure that the system is evolving is expressed by the proposition here. It is time to try it out for ourselves. Let us remind ourselves of the program graph for factorial and the semantics that we gave to the individual actions. First, determine whether or not the factorial program constitutes a deterministic system. Next, determine whether or not the factorial program constitutes an evolving system. It is important to stress that the simple tests for being deterministic and evolving are sufficient but not necessary. Consider the following simple program. Starting at the initial node, if x is 0, we take the path to the left and reach the final node with y being 0. If x is positive, we take the path to the right and reach the final node with y being 2. If x is negative, we take one step to the right and one step to the left and reach the final node with y being 1. The system is deterministic, but the simple test for checking it does not hold, because the node before the branch on the sign of x has two ways to go if x is 0. What saves the day is that this node is never reached with x being 0. Similarly, consider the following simple variation of the program we just looked at. The test on the sign of x has been replaced into being strict tests. Once more, the system is evolving. If x is 0, we continue to take the path on the left and reach the final node. If x is positive, we continue to take the path on the right and reach the final node. If x is negative, we take a step to the right and a step to the left and reach the final node. However, the simple test for checking that this is an evolving system does not hold, because a node before the branch on the sign of x has nowhere to go if x is 0. What saves the day is that this node is never reached when x is 0. You should now read the section in the book doing the try-it outs on the way.